For my physics project, I chose to explain the physics of a yo-yo. I mean, a yo-yo seems like a pretty simple toy, but there's actually some really complex physics behind it. A yo-yo itself is comprised of 3 cylinders, 2 of which are equal mass and radius on the outside to balance it out, and 1 of which runs through the middle, which is of a different mass and radius. But the cylinders themselves are equally distributed as to keep the yo-yo balanced at all times. So there's a lot of mathematical concepts that actually work behind a yo-yo. So I am going to describe them today. So I thought I'd start with the hardest one, which is the moment of inertia. The moment of inertia, for those of you who don't know, is the rotational analog for mass. So where mass is to acceleration and force, this moment of inertia is to angular acceleration and torque. So that's the analog. So the reason that it's not as simple as you would think to find the moment of inertia is because there are 3 parts. So what I'm going to do is write a general equation, and then I'll be able to use it for all 3 cylinders. And you'll see here the mass of the 2 cylinders on the outside are different from the one on the inside. The width, L is going to be the width today, of the 2 cylinders is different from the one on the inside, and the radius of the ones on the outside are different from the ones on the inside. So using these general variables, we can come up with one equation for cylinders and apply it. So for those of you who don't know, the formula for for a moment of inertia is the integral of r squared dm. Now the problem with this equation is that r and m can't be integrated together. They're different variables. So we need a bridge between the 2. So we're going to use rho. I'm going to have rho equals density, which is mass over volume. Now volume is equal to, in a cylinder, pi r squared times L, L being the width. So, and to clarify, this L is not the same as this L. This L is rotational momentum. So, this L being width, we can use this to get P equals M over pi r squared L. And since we're using the integral, and since the entire thing is equally distributed, so the mass throughout the entire cylinder is equally distributed, we can generalize this we can actually specify this equation to use it as the instantaneous at this particular moment, and then later on generalize it again for the entire cylinder. But right now we can change this and make it P equals derivative of the top over the derivative of the bottom. So dm over 2 pi rl dr. And so we can write this as dm equals rho times 2 pi rl dr. And now that we have a dr, we can substitute back in, use substitution, and integrate this. So we can write this out again as rho times 2 pi l times the integral of r cubed dr. What I did was combine like terms. So we can integrate this and get rho times 2 pi l times r to the 4th all over 4. And that gives us a general equation. So now what do we do with this? We need to get rid of the rho in order to get a regular equation. So remember that we wrote this out earlier, and I said that we could generalize this again. So what we can do is substitute this for m times 2 pi l times r to the 4th all over 4 times this, which is pi r squared times l. So the l's cancel out, pi's cancel out, this goes to 2 and this cancels out, this goes to 2 and this cancels out. And that leaves us with m r squared all over 2. So that's a general equation for I. And now to find the total moment of inertia, since we're measuring it from the center axis, the center on which it's spinning, we can find the total moment of inertia by adding up the sum of the three cylinders. So we can have M1 and R1 for the first cylinder, M1 and R2 for the second cylinder, and M2 and R2 for the second cylinder, and M3 and R3 for the third cylinder. But since the first cylinder and the third cylinder, and the second cylinder, in this case, the way I defined it, are equal, we can really write that as twice of the first one. So it will be M1 times R1 squared over 2 times 2 plus M3 R3 squared over 3. And so that's going to be the moment of inertia. So I, and I'll write it down here again, I equals M1 R1 squared plus M3 and I just wrote that, R3 squared all over 2. And that's how you find the moment of inertia of a yo-yo. So next, I'm going to focus on the energy that's involved in a yo-yo, and I'm only going to focus on the mechanical energy. I know that in real life there's some friction and there's some sound that are expelled from the yo-yo, and that's a loss of energy, but that's really, really complex. So to help you understand, I'm just going to stick with the theoretical method, which is perfect world. Frictionless, soundless, spinning perfectly, energy conserved. So in the case where energy is conserved, potential energy initial is equal to kinetic energy final. And I'm defining the height, in this case, to be the length of the string. So we're going to pretend that when the yo-yo is released, it's just going to go to the floor. And since it's frictionless, it won't be hurt, or it won't be stopped anyway. So first of all, potential energy. This one's actually kind of simple, because potential energy is equal to mgh, where m is the mass, g is the acceleration due to gravity, and h is the height. So since I defined h already, and I defined m naught, the total mass, earlier, and g is a constant, the potential energy is actually going to be m naught times g times h. So that's the potential energy. Now, that's potential energy initial, when it's not moving yet. The kinetic energy is a little bit more difficult, because the potential energy initial equals the kinetic energy final. So the kinetic energy final, and that is something that you can use later if you want to do this with numbers. You can set what we're about to find equal to this, and use that to find the actual number values. But for now, we're just going to deal with this. So the kinetic energy final is going to be equal to the sum of the translational and rotational components. So the translational component is half times mass times velocity squared, and the rotational component is going to be half times I times omega squared, where omega is the rotational velocity, so they're analogs for each other. So this is a little weird, because in order to find this, you have to think about it as a free body diagram. So that's going to be the yo-yo, this is going to be tension, and this is going to be the force due to gravity. So, because those are the only forces acting on it, and the object is accelerating constantly, because there's no like jerk or anything, we can just use the net force to find the net acceleration to find the velocity. So, F net is going to be equal to, just the net force is down, we're just going to consider that the frame of reference. The force due to gravity is going to be the mass times acceleration due to gravity minus tension. So A net is going to be equal to mg minus t all over m, because force is equal to mass times acceleration, so acceleration is going to be equal to force divided by mass. So now is where it gets kind of tricky, because in order to do anything further, we have to do torque. So first of all, I'm gonna set a frame of reference here. When considering a yo-yo that's moving, we have to be really specific about what we're considering and when we're considering it. So in this case, when this is speeding up in the angularly, rotationally, the only thing that's acting on it is the string, and the string is acting specifically on the inner cylinder. Well, when we consider the moment of inertia, we have to consider the whole thing. So in some of my calculations, the ones where I'm dealing just with tension, I'm going to be specifically referencing the inner cylinder. But then when I'm trying to generalize it, I'm going to have to go back to dealing with the whole thing. So what we have to do is use torque. I'm going to move over here. Torque is equal to FR sine of theta, but we don't need to deal with the sine of theta because it's a circle. It's also equal to I, which is the moment of inertia, times alpha. And then the rest of my calculations, I'm just going to try to stick with I because it's going to be really messy to deal with all of that. And since you already know what it is, you can just do the algebra and find the proper answer. But this is going to be easier to understand. So we have this here. The force we're dealing with right now is tension, because that's the only force besides gravity acting up, so that's the force producing torque. So tension times the R, which in this case is going to be the one with the inner cylinder, R3, is going to be equal to I times alpha. And alpha, in this case, because A is actually equal to, this is a bridge, alpha R. So alpha is going to be equal to A over R. So it's going to be I times A over R. And remember, specifically because we're dealing with R3, it's going to be R3. And this should be on the bottom. So now that we have this, we can solve for tension. I alpha over R3 squared. And we have this equation back here, which is for acceleration. And I'm sorry, this is not alpha, this is A. So we have A equals mg minus t over m. And we can plug this in to get A equals mg minus I A over R3 squared over m. And so now what we can do is we can just cancel to make it easier. A equals g minus I A over mr3 squared. And this is okay, except for the fact that we have an A on both sides. So in order to get a real value for A, we can't have the same variable on both sides, so we need to simplify. So what we need to do is move this over to that side, pull the A out. So that's what we're going to do. A equals, actually not A equals, I'm sorry. A plus I A over mr3 squared equals G. A times 1 plus I over mr3 squared equals G, and A equals G over all of that, which is 1 plus I over mr3 squared. So now we've crossed off a couple of things on the list. We found A, we found I, and we can use A to solve for kinetic energy. The thing is that there is another bridge that we're going to use in a second. I'm going to go ahead and tell it to you, which is V equals omega, angular velocity, times R. V over R equals omega. And remember, we're considering only the inner cylinder accelerating at this point, and the moment of inertia is the entire thing. So we have A, and we know that because of the particular situation, the acceleration is constant. So we can use our kinematics equations to find the velocity We can use the velocity to find angular velocity, and we can get a more proper equation for kinetic energy. So what we can do here is v squared equals v naught squared plus 2ad, which is a kinematics equation. So that means that since v naught is 0 because it starts from rest, v is actually going to be the square root of 2ad, and we can actually replace d with h because we defined it as the bottom part, and we were trying to find the velocity at the bottom. So we can replace that with h and have a velocity equation. And I don't want to plug it in just because it will get complex, but you already have a value for a right here. So when you're doing the equations, you use this value for a, you use that value for I that we found earlier to get the actual answer. So now that we have this, we're going to go back to that equation. K is going to be equal to 1/2 m times 2ah because of this. We can substitute back in for the v squared, the square root of 2ah, and when that squared it becomes 2ah, plus 1/2 times I, which we found earlier, times omega squared. And so since omega is this over r, it's going to be 2ah over r squared. And that is our formula for kinetic energy. So using our combination of equations, rotational, translational, kinematics, force equations, we were able to cross off most of the things on our list. We were able to get the moment of inertia, we were able to get kinetic and potential energy, we were able to get acceleration, we were able to find velocity, we were able to find, we used the bridges, so if you use the bridges you can find the angular acceleration and velocity, which is not that hard. You just take the acceleration and velocity you found and divide them by r. So the only things left on the list to explain the motion of a yo-yo are momentum, both angular and translational, which really aren't that hard because angular momentum is equal to I times omega, and linear momentum is equal to mass times velocity. So we've already found the I previously using that big long equation m1 r1 squared plus m3 r3 squared all over 2. So we found the I earlier. We found the velocity and we have the acceleration to plug in there. So that would get kind of complex if you plugged it in, but you can do it to get the actual value and use the bridge to find the value for this. And again, for this, you just plug in the A. So really, we found all of the mathematical components. But there are a couple of other things that describe the motion of a yo-yo. There's friction and there's sound specifically. And I said earlier for the calculations we're not going to discuss them, but they are kind of important because of the fact that yo-yos are based on friction. When they are on their way down, they don't want friction. You don't want friction. You want them to spin as much as possible and as freely as possible. But once it gets down, it'll spin freely. So you want it to have some friction, or else you can't get it back up. So friction is actually a really important part of the yo-yo, and is sound as well, because they're both energy escaping. So you only want to have the two when you absolutely want to. So that brings me to the next part of this, improving a yo-yo. This particular yo-yo, if you can see here, uses a sort of clutch that flips on and off. So you can either have it on auto return, where it'll get to a certain speed of spinning, it'll come right back up, or you can have it on regular mode, which is what a yo-yo is supposed to be, where if you turn it off, it will go down, keep spinning until you want it to come back up, and then if you can get it to catch, it'll come back up. So what I thought was the best way to improve yo-yo maybe just to improve on that clutch. Rather than having the yo-yo slip to sleep at the bottom when the clutch is on, so like here it'll come back up, but if I throw it down hard enough, then it'll sleep. I'll show you that right now. When you throw it down hard enough, it does this, or once it slows down enough, it'll come back up. So rather than have a simple clutch that has it slip and then slow down enough where the friction will catch, my idea is to have the string actually like attached to the center cylinder, so that instead of slipping, it will be the entire cylinder rotating. So the cylinder itself will not be a true cylinder, it will be locked into the left and right cylinders, the outer ones. And at the bottom, there'll be a sensor inside of this, which will detect when the tension is greater than the weight of the yo-yo. Because when it gets to the bottom of its path, the tension is momentarily greater, because all through here the tension is less than or equal to the weight. At the bottom, when it's spinning, when it's sleeping, it'll be exactly the weight. But at that moment, when it's changing from moving to at rest, it will have a tension greater than the weight. So there'll be sensors in this that can detect when the tension is greater. And what it will do, it'll have this clutch system, but it'll be different. It'll unlock whenever the tension is greater than the weight. So it'll make it more efficient, because rather than having a mechanical system, you can have a computer that can detect it, and you can use materials that are more frictionless. So you can have a better, longer sleep and have it easier to return to your hand, because when you pull back up, the momentary increase of tension will cause the clutch to turn back on again and pull it up. So it'll be easier to use, it'll be better for tricks, I think, and it'll have less friction, improving the efficiency of the yo-yo all around.